Today we're going to be talking about geometric sequences. We're going to start first with our vocab. A geometric sequence is basically a sequence of numbers whose change occurs from multiplying to get to the next term. A common ratio is the actual number that is being multiplied. All right, so first thing we're going to do is we are going to look at some sequences and we're going to determine if it's an example of a geometric sequence, and if it is, we're going to identify the common ratio and the next two terms in the sequence. So looking at example number 1, I see a sequence of 5, 8, 11, 14. So the first thing I'm going to do is try to determine how am I going from 5 to 8. Since it's increasing, there's only two ways I can do that. I can do it by adding or multiplying. So I'm going to start first checking the addition. 5 to 8 would be adding 3. Now I need to see, is that true down the rest of that sequence? 8 plus 3, yep, it is 11. And 11 plus 3, yep, that's 14. So I am adding 3 each time to get to the next number. So no, this is not a geometric sequence. Since it's not a geometric sequence, I do not need to continue the sequence or list a common ratio. All right, looking at number 2, I'm going to look from 2.5 to 5. Again, that's increasing, so I can only do that by addition or multiplication. Well, if I was doing it by addition, I would have to add 2.5. And then I would need to check, does 5 plus 2.5 get me to 10? The answer to that is no. So that is not going to be the correct method. So then I have to say, okay, well, what would I multiply by? 2.5 times 2 would get me to 5. Well, is that true? 5 times 2 would get me to 10? Yes. 10 times 2 would get me to 20? Yes. So yes, this is a geometric sequence because I'm multiplying to get to the next term. My common ratio, which we're going to abbreviate with CR, is the number that I multiply by. So that is my 2. And then it asks me to continue my sequence. So 20 times 2 would be 40, and 40 times 2 would be 80. It only wanted me to go 2 more places, so I'm done. Okay, number 3, I have 17 to 13. This is decreasing. So because of that, I can only do that by subtracting or dividing. So I'm going to first see by subtracting. 17 minus 4 would be 13. Is that true? 13 minus 4 to get 9? Yes. 9 minus 4 to get 6? No. So then I could check, okay, let's see if I divide by something. Now, when I do division in sequences, I'm actually not going to write it in terms of division because I would not be able to tell the difference between a division of 2 and a multiplication of 2. And so because of that, we always write our change by multiplication. We'll never write our common ratio in terms of division, ever, ever, ever. And so we're going to think, what do I have to multiply by to get to the next term? But it's going to be multiplying by a fraction. And the fraction is always going to be this second term on top divided by that first term on bottom. So if I do 17 times 13 seventeenths, I would get to 13. Well, so then I need to see, does 13 times 13 seventeenths get me to 9? The answer to that is no. So therefore, there is actually no common pattern here. And so I am just going to write no. And there's no common ratio to list because I'm not doing the same thing from term to term. All right, number 4, we're going to look to see how is it changing from 5 to negative 5. That is decreasing, so it's either going to be subtracting or it's going to be in terms of multiplication. So 5 to negative 5 would have to decrease by 10. But then it goes from negative 5 to positive 5. So that is not true. That does not work. So I'm going to look at what could I multiply by to continue the sequence. Now remember, we always said we're going to multiply by the second term divided by that first term. Well, I can actually simplify that. -5 divided by 5 is a -1. So I'm going to change that to a -1. I'm going to look to see, does that continue? -5 times -1 gives me +5, so that worked. And 5 times -1 gives me -5, so that worked. So my answer is yes, it's geometric. The common ratio is going to be -1. And the next two terms would have to be +5 and -5. Number 5. So I can see from 81 to 27, this is decreasing. So again, it's either going to be subtraction or multiplying by a fraction. So I'm going to start first with subtraction. 81 to 27 is a difference of 54. And then if I go from 27 to 9, that is not a difference of 54, so that did not work. So now I'm going to look at what could I multiply by to make this work. Again, I'm going to take that second number, 27, divide by my 81. This can actually simplify to 1/3. So then I'm going to look, if I do 27 times 1/3, do I get to 9? The answer to that is yes. And if I do 9 times 1/3, does it get me to 3? The answer to that is yes. So yes, this is geometric. My common ratio is 1/3. So I want to point out one thing. If I go back to the original sequence, hopefully you can see that if I looked at this and I thought of it in terms of division, I could say 81 divided by 3 would get me to 27. 27 divided by 3 would get me to 9, and 9 divided by 3 would get me to 3. So in other words, I can always take this divide by 3 and I can convert it to a fraction. If you think back to middle school, if you remember that keep, change, flip, I can make this be multiplication by changing it to multiplication and flipping that fraction. So that would become times 1/3. So that can also help you determine that common ratio if you visualize it in terms of division and then flip that fraction. Ultimately, when you write your common ratio, though, your common ratio has to be in terms of multiplication. So if my sequence is going down, it should be multiplying by a fraction. And I'm going to continue that pattern. So 3 times 1/3 is going to give me 1, and 1 times 1/3 gives me 1/3. Last example like this, you can see 8 is all the way across. So this is not increasing, but what I can say is that I am multiplying every term by 1 to keep it the same. So that would be geometric, and the common ratio is 1. So the next two terms would be 8 and 8. You're never going to say a change is by adding 0. Instead, we'll always make that be a geometric sequence of multiplying by 1. All right, the next type of problems that we're going to deal with are going to involve recursive definition. And if you remember, we actually saw something super similar to this back when we talked about arithmetic sequences. So the only real difference here is now I actually see a times r at the back of both of those equations. We used to have that as a plus d, which was adding our common difference. Now it's times r to be multiplying by our common ratio. So let's recap what all of this means, because it kind of looks like a foreign language. Remember, they ultimately mean the same thing. So F1 and A1, these two things are standing for the same thing, and that just stands for the first term in my sequence. Now, the Fn or the An just stands for the value of the term we're looking for. Or sometimes you hear that as the nth term. You can also think of that as the next term in the sequence. Now, f of n minus 1, or A n minus 1. This is just saying the value of the previous term. And R, I already told you, is going to stand for our common ratio. Now, if you think about it, this should now make sense. This first part up here is saying the value of my first term is what number. Then this bottom part is saying the value of the next term is equal to the value of the previous term times my ratio. And that should make sense to you. It's just a more difficult way of writing that. All right, so let's look at some problems that are going to involve the recursive definition. We're going to start first with number 1. We're given a sequence and it wants me to actually write the definition. So the first thing I'm going to do is I'm always going to identify the first term in the sequence. So the first term in function notation, it's always written with an F, and we put a 1 in the parentheses to represent the first term. Okay, the first term in my sequence is a 7, so I'm going to put equals 7. Now I'm going to determine how are my values changing. How am I going from 7 to 21? And that is a change of multiplying by 3. Double check, is that true all the way across my sequence? Yes, it is. So I know that that must be my ratio. So the next part of my recursive definition is I'm going to have f of n equals f of n minus 1. That will always be there. Every single time you have to include all of that. The only part that's going to change is I'm going to bring that times 3 down into that equation. Now the same will be true for subscript notation. The only difference is instead of an F, I use a lowercase a, and instead of parentheses with the 1, I use a subscript 1. The first term is still 7. And then again, I'm going to have a lowercase a with a subscript n equals a lowercase a with the subscript of n minus 1. And then I'm going to tack on that times 3. And I am done. We need all of those pieces in order to actually write the full recursive definition. I cannot actually use the bottom equation if I don't know what my starting term is. So I have to have the f of 1 equals 7 so that I know where I'm beginning my sequence. All right, now let's look at an example going in reverse. I'm going to give you the recursive definition, and now we're going to actually come up with the sequence and find the indicated term. So it says find the indicated term of the geometric sequence using the information given. So I'm always going to start first with f of 1 is 15. That tells me my first term is 15. Okay, then it tells me f of n equals f of n minus 1 times negative 2. Really, all that I care about out of that is times negative 2, because remember, that's my common ratio. So with that, I know how my values are going to change in my sequence. Now, what's really important is this last piece, f of 4. This is telling me it wants the fourth term in my sequence. Whatever the number inside the parentheses is what term it's asking for. Now, a common mistake a lot of students make is they don't count 15 as the first term. Remember, this is my first term. So then I have my second term, I have my third term, and then I have my fourth term. And when I get to that last blank, that will be my value. So remember, my common ratio is times negative 2. So that's what I'm going to apply to get to the next term. 15 times negative 2 gives me negative 30. Negative 30 times negative 2 gives me positive 60. And 60 times negative 2 gives me negative 120. So the value of the fourth term is negative 120. So we're going to write f of 4 equals to negative 120. Okay, we have a couple more before we move on to our last type of problem. Number 3, it says find A7 if A1 is negative 10, A2 is 20, and A3 is negative 40. So remember, this little number as a subscript tells me what term that is. So this is telling me the first term, this is telling me the second term, and this is telling me the third term. And since it says find a 7, we want the 7th term. So first thing I'm going to do is I'm going to create 7 blanks. And I know that once I fill that last blank, I have my answer. Now I'm going to fill in what I know. We know the first term is -10. We know the second term is 20. And we know that third term is -40. Now we got to figure out what is our common ratio. How are our values changing? And this is going from one term to the next by multiplying by -2. If you get confused and you don't remember I can always take that second term divided by my first term. And that would give me my common ratio. Now I'm going to continue that pattern. -40 times -2 gives me +80. 80 times -2 gives me -160. -160 times -2 gives me 320. And 320 times -2 is -640. All right, looking at number 4, it says a sequence can be generated by using AN equals 4, AN minus 1, where A1 is 6 and N is a whole number greater than 1. What are the first 4 terms in the sequence? Now, this is another way of just saying AN equals AN minus 1 times 4. We can actually take that common ratio and just put it in front of the AN minus 1, and it will mean the same. Important thing here is it says A1 is 6, so we know the first term is 6. And we know that our common ratio is 4, so we're multiplying 4 to get to the next value. Well, 6 times 4 would give me 24. Based off of that information alone, I know that my answer must be A. It's the only one that shows 6, then 24. All right, our last type of problem, we are going to write an exponential model for data. That's basically just asking us to write the exponential regression. And remember, exponential regression is when we either use our stat edit on our TI-84 or where we input our table onto Desmos and we ask for it to calculate exponential regression. Now, there's one important thing to note about exponential regression in Desmos. It's only for exponential. This doesn't apply when we do quadratic or linear. But when I do exponential regression on Desmos, there's going to be a button that appears that says log mode, and you must have that checked in order to get the correct exponential equation. I'm going to type this into Desmos, and I'm going to then click the little scatter plot button out to the side, and I'm going to select exponential regression. It tells me right here that it's exponential. Then I'm going to make sure I click the log mode button, and then I'm just going to copy that equation down. If needed, I can round to the nearest hundredths. So I'm going to say y equals 74.88 times 0.62 raised to the x power. So this equation represents the best fit exponential graph for this data.